Thank you to the chair for the introduction, and thank you to the conference organizers for inviting me to give this talk. Today I will talk about what we have done recently on using AI for earthquake engineering. My background is in civil engineering, so my main interest is how we can actually generate structural objects using AI technology. We are moving through 3 stages, from prediction, to design, and then to autonomy. This is the outline of my presentation. I will first explain why we are doing this work, then introduce the 3 stages one by one, and finally give a conclusion. Professor Wang, previous speaker, has already demonstrated a very good example of why we need AI for prediction. It can make prediction more accurate and more efficient. But as engineers, we do not only want to predict something. We also want to generate something, and eventually to build a real-world project. Therefore, AI generation helps us generate engineering designs, while AI agents can go further and help us complete the demanding work across the whole process. First, AI prediction belongs to the broader topic of AI for science. Many engineering problems involve very complicated and time-consuming computations. After training, an AI model can perform selected simulations much more efficiently, while still providing the accuracy required for the engineering task. Now we are all familiar with generative AI. We can see that AI can generate a human face that looks like a real person. So why can AI not generate a design drawing? After learning from many engineering drawings, it should also be able to generate a design drawing that looks like one produced by a real engineer. This is the fundamental idea of AI generation. When we move to a real-world project, however, we need to go through many different procedures. We can therefore use an AI agent to connect these procedures and help complete the design, computation, and verification. This is why we need the 3 stages of prediction, generation, and autonomy in earthquake engineering. Now let us go through these 3 stages one by one. I will begin with AI prediction. At the beginning of this research, many researchers, including ourselves, developed end-to-end machine learning prediction models. We collected ground motion data, structural parameters, and response results as labels, and then trained machine learning algorithms to predict structural responses. This type of work has 2 major problems. First, in real projects and physical experiments, the number of components we can test is very limited, so the experimental data are usually insufficient for training AI. We can use simulated data, but the simulated data may not be accurate enough. Second, a purely end-to-end machine learning procedure does not explicitly contain physical rules, so its predictions may violate physical laws. We therefore carried out several studies to address these 2 limitations. First, we proposed new models for simulating the hysteretic behavior of structures under earthquakes. For example, our adaptive weight LSTM method combines several relatively simple models to predict complicated structural behavior. We also proposed a new training strategy that reduces the amount of component data required for training to about 1/16 of that used by the previous method. This makes the model more suitable for real situations in which sufficient experimental data are not available. For physics-informed AI, we proposed multi-scale surrogate models at the continuum scale, the individual structure scale, and the urban scale. These include a multi-resolution hash encoding solver, a physics data hybrid model, and a building region coupled graph neural network. With these methods, we can make the computation more than 2 orders of magnitude faster than the traditional approach while maintaining the required accuracy in the reported tasks. We proposed a unified ground motion prediction model for intensity estimation, earthquake early warning, and ground motion interpolation. It is based on a mask transformer, and we trained it using more than 4 million ground motion records from California. One model can therefore support several different ground motion prediction tasks. With this unified model, the ground motion prediction accuracy is improved by about 10% compared with the mainstream non-ergodic models used in our study. For earthquake early warning, the model can reach the accuracy of the final U.S. shake alert report within 3 seconds after P-wave arrival. It can also use newly observed station data to update the prediction. We can go one step further. In addition to encoding the ground motion and the site, we can also encode the fault. We therefore developed a transformer-based discrete fault encoder that includes fault geometry. Compared with a point source model, this model gives better accuracy, especially in near-fault areas. In the comparisons shown here, the prediction error is reduced by 36%. These are some examples of our work on AI prediction. Now let us move to AI generation. As I mentioned before, after learning from many design drawings, AI can generate a drawing that looks like one produced by a real engineer. Earlier methods used models such as GANs, graph neural networks, and diffusion models for this purpose. But this is still a purely data-driven approach, and we believe it has an important limitation. It mainly guarantees similarity between the AI-generated design and the designs produced by human engineers. When we carry out a real design, similarity is not enough. We need engineering knowledge. For example, the design must satisfy code requirements. As structural engineers, we also need to embed mechanics into the AI algorithm to guarantee structural safety. Therefore, we need to integrate both knowledge and mechanics into generative AI in order to create a generative method that can actually be used for engineering design. The next challenge is how to formulate a mathematical model for this knowledge and mechanics integrated algorithm. If we look at the conventional generative AI formulation, we can see that it is purely data-driven. It can make the generated data, y star, similar to the training data, y, but it cannot by itself guarantee structural safety or code compliance. We therefore proposed a knowledge and mechanics integrated generative AI method. We add a constraint function, C, to both the training objective and the generation objective. By changing this constraint function, we can require the generated structure to satisfy code requirements as well as structural performance requirements. The figure on this slide shows the basic mathematical idea. Here is an example. The input is an architectural design drawing, the gray lines represent walls, and the green lines represent doors and windows. The engineer's design is shown as the reference, with the red lines indicating the shear wall layout. I can generate a shear wall layout that is very similar to the engineer's design. In earlier stage of this research, we can see some local defects in the generated result. But by using the latest model, the design is not only similar to the human design overall, but also more reasonable in its local details. Because mechanics and engineering knowledge are included, the generated design can change together with the design conditions. For the same architectural layout, when the design peak ground acceleration is 0.1 g and the building height is 30 meters, the shear wall layout is like this. If we increase the height to 100 meters, the layout changes. If we then increase the peak ground acceleration to 0.2 g, the layout changes again. We can see that, as the design conditions become more demanding, the model generates more shear walls and a different wall arrangement. In other words, AI connects the design conditions with the final generated result. In addition, when the length or thickness of a shear wall changes, a surrogate model or a differentiable finite element model can predict how the flexural and shear stiffness will change. This differential information can guide the layout generation. In the 18 test cases shown here, the the proportion satisfying the inter-story drift ratio check increased from 77.78% to 100%. Here are several typical examples of beam layout design. For a complex shear wall building, even an experienced engineer needs time to find a feasible solution, while AI can generate a solution that is very similar to the engineer's design. For the irregular frame shown here, the engineer uses a secondary beam to connect the two parts, while AI finds another solution and uses a main beam directly. In this particular example, the AI-generated solution provides a more direct load path. We did not only publish these algorithms in papers, we also implemented them on an online platform so that people can use them. For the supported design workflows, the system can improve design efficiency by more than 10 times. According to the platform statistics shown in this presentation, it has already been used in more than 7,000 real-world projects and adopted by more than 100 organizations. This is project number 5034, completed recently. It is a shear wall building with a design peak ground acceleration of 0.1 g and a height of 57 meters, and the AI-generated design passed the code checks implemented in the software. This short video demonstration shows how the program works. First, you input the design conditions and select the architectural drawing. AI identifies the architectural components and starts the structural design. After the design is finished, the software performs the calculation and gives the structural performance indicators. You can then start an optimization iteration and obtain an improved result, together with the concrete and shear wall quantities and the performance of the whole structure. This is AI-powered structural design. With only several mouse clicks, a design can be generated in minutes. The technology is not limited to building structures. We have also explored its use in dam design, photovoltaic support design, bridge design, fire sprinkler design, integrated architectural and structural design for detached houses, and special equipment design. These applications are at different stages, but they show that this technology can be extended to many engineering fields and can help improve structural design efficiency. Now we go further to AI autonomy. Once we found that AI could perform a design task, a new challenge appeared. A real design contains many different steps. We therefore need AI to connect all these steps and make the entire process more efficient. For this purpose, we developed a new system called StructureClaw. Instead of generating only one isolated result, it connects design generation, structural analysis, verification, and revision. The aim is to let the agent complete the workflow while keeping the intermediate results and engineering evidence available for checking. At the beginning of this year, there was a strong wave of interest in OpenClaw, because people believed that this type of agent could help us complete many tasks. StructureClaw was developed independently by our team, but we borrowed the name from OpenClaw so that people could immediately understand its agentic focus. The key idea is to bring planning, tool use, and iterative feedback into structural engineering. StructureClaw is a React-based agent that integrates engineering skills and structural analysis tools. You provide the structural design requirements, together with drawings or other project information. The agent then organizes the task, implements the design procedure, calls the required engineering tools, and produces structural models, analysis results, checking evidence, and reports. During the workflow, it repeatedly reasons and acts rather than simply generating one answer. This is different from conventional software that follows one fixed sequence step by step. At every stage of the design, the AI checks whether the input is complete. If important information is missing, it communicates with the user and asks for clarification, so that it can fully understand what the user wants before moving to the next step. It then observes the result of each action and decides whether it should continue, revise the model, or ask another question. In this workflow, we separate skills from tools. Skills mean understanding what the user wants, identifying the engineering constraints, and implementing the work conventionally carried out by structural engineers. Tools mean calling professional software to complete specific tasks. For example, the agent can call OpenCs for structural analysis, or PKPM and similar software for reinforcement and detailing design. The agent is the framework, while these professional tools remain essential for completing the engineering work. There are now many AI agents in the world, but how can we evaluate their engineering performance? We therefore proposed a benchmark called StructureClaw Bench. The current version shown in the PPT contains 50 standard cases, 50 interactive cases, and 50 multimodal cases. The cases cover tasks such as steel frame and concrete frame design, different input languages and formats, missing information, and changing user requirements. We use these cases to compare different large language models and to test whether the agent can select the correct structural type and skill, complete the workflow, and produce an executable engineering artifact. The comparison shows that, when we use StructureClaw, the system can complete the benchmark tasks with an average success rate of 88.6% under the tested configurations. With the conventional prompt-based method, where the user pushes the model forward step by step, the average success rate is 56.8%. So in this benchmark, the agent and skill-based workflow makes the success rate substantially higher than generic prompting alone. Another important point is that StructureClaw is completely open source under the MIT license. Everyone can use it, modify it, and contribute to it. We are still working on the system, and the community statistics on this slide show the participation achieved by the time of this presentation. You are very welcome to join the community and help make StructureClaw more and more powerful. Finally, let me come to the conclusion by looking again at the workflow of structural seismic design. We are engineers, and this is the general workflow of structural design: seismic loads, structural design, mechanical analysis, code checking, and finally reports and drawings. If we look at individual stages, AI prediction can help with the analysis. Much of routine structural design uses linear elastic analysis, so these tasks are comparatively easy for AI. We can also use AI generation for structural design. Many of our drawings are two-dimensional, so two-dimensional generation provides a practical starting point. If we look at the entire procedure, it is a mature closed-loop workflow, and an AI agent can connect the individual steps. Therefore, AI-based seismic design is well aligned with the mainstream direction of AI research. From an AI research perspective, many routine stages are relatively structured and verifiable, so I believe AI-enabled earthquake engineering has a very promising future. That is all for my presentation. Thank you very much for your attention, and I welcome your questions.